Okay. So a three-body problem is any problem in classical mechanics or quantum mechanics that models the motion of three particles. The gravitational problem of three bodies, in its traditional sense, dates back to 1687 when Isaac Newton published his Philosophy Naturalis Principia Mathematica. In this, he took the first steps in the definition and study of the problem of the movements of three massive bodies subject to gravitational attraction. He also took the first steps in applying his results to the lunar theory, the motion of the moon under the gravitational influence of Earth and the sun. And thanks to Isaac Newton, we can write a set of equations to describe the gravitational force acting between bodies. I think I included the math down here. I decided to do a restricted three-body problem of the sun, Earth, and Venus. For this project, we will simulate the motion of the Earth, Venus, and Sun gravitational system as described by Newtonian mechanics. For simplicity, we will restrict the problem to the following case. All bodies start off collinearly, motion is restricted to a plane, and gravity is the only acting force. So I didn't really want to deal with the chaotic n-body problem, where almost every possible case is unpredictable on long time scales, and each has an astronomically large range of potential outcomes dependent on the tiniest of differences in position and velocity. So I decided to do a restricted three-body problem of the sun, Earth, and Venus. And as for our solar system, thankfully we can have reasonable confidence and in its stability for at least the next several 100 million years, but who knows? If another star launched across from another galaxy is on its way to us, who knows? But hopefully we don't have to deal with that. Anyhow, so the mathematical statement of the three-body problem can be given in the terms of Newtonian equations, which I have included down here, for vector positions xi, yi, and zi of three gravitationally interacting bodies with masses. And they can also be stated equivalently in Hamiltonian form, which we've been learning in class. And my sun, Earth, and Venus system is a restricted three-body problem where their motions are given by these equations with the planetoid, each planetoid motion is given by these. So let's go to my code. I ran my code. And so for the first segment, which says import some magical dependencies, this one will import the numerical libraries as well as the animation libraries that we need to do the actual project. For the second block of code, where it's called the problem setup, right here, what we first do is we create a class called space body, and this will be a conglomerate of information that will store the data of an individual planet or a star. It basically stores all the information you need to know from an individual object in space. The underscore init right here stands for initialize, and what it does is that it'll grab the mass and store it inside an instance variable called self.m, which represents the mass variable of that object. The next one, position, it'll convert that into a NumPy array for numerical calculations, and it will store that in self.r for like position to represent that. And then for velocity, we're not going to be storing velocity directly. We are going to be storing the momentum of the object. So we first convert it into a NumPy array called np.asArray here. And then we multiply that by the mass of the object to get the momentum. We have another function of which all of these space bodies have, which is called force on. So what this does is that given an object, it will calculate the force that object exerts on another object. So in this case, the other object that it will be exerting a force on is the body. So r hat is the vector for which this force will be directed. R3 is the magnitude of the radius cubed. Fg will be the force of gravity. Space body.g is the universal gravitational constant. So I multiply that by the masses of the two objects self.m and body.m, and then we divide that by R3. If you notice, whenever you search up the magnitudes of the force of gravity, it's going to be the masses multiplied by each other divided by R squared, not R cubed. The reason why we have R cubed here is because that extra R is going to normalize the R hat. Since the formula for the force of gravity gives you the magnitude, and we need to convert that into vector form. And since normalizing a vector is calculating the difference of 2 points, and then you divide by the magnitude of that distance. So you can just grab that 1 over r and shift that over to the coefficient and divide by r cubed now to make it more computationally stable. And finally, the next function is called update here, which grabs that force vector applied on the object as well as the time step, and it will update the momentum first. So self.p plus equals the force times dt is just standard, right? And the momentum is calculated by the force times the change in time. And then given that, we calculate the position by adding on to the current position. And the momentum divided by the mass multiplied by the time displacement dt. The momentum is, yeah. So the actual initialization is seen at the bottom right here of this block of code. The masses are the first term, and the position is a pair of numbers, which you see as a pair of numbers which represent the x and y coordinates, the second term. And the third term, the last pair of those numbers are the velocity of the object. And in this case, the velocity of Venus and Earth are calculated to be the orbital velocities. And so now here we have the next third block of code is called the physics engine. This part of the top says, that says like x underscore Earth, x underscore Venus, x underscore sun. This will be storing the coordinates of these planets as you're simulating the entire orbital system. This will be the data objects that are storing all that information. The limit variable that you see is the limit as you're plotting the graph, referring to the minimum and maximum y and the minimum and maximum x. So then the dt right here, the time step is quite large. It's 8,000. The reason why we have it so large is because the units are in seconds. But if you remember, planets don't really orbit in a reasonable number of seconds. They take years to do a full orbit of the sun. And then we have a simulate function, which will actually do the full simulation. So first, right here, we have, well, first what we have to do is calculate the force that each object exerts on the other. So we don't actually need to calculate each individual pair, for instance, sun on Earth and Earth on sun, because the force applied on the sun is just the same as the sun applied on Earth, just negative because they're in opposite directions. To calculate the net force right here, now we use that observation that some directions will just be the opposite depending on which one is acting on the other, which is why you'll see that some of these forces have a negative sign on them when we're calculating the net forces. So now that finally that we have these net forces, we're going to update the positions. The positions of the sun, Venus, and Earth using the update function and the time step. After that, after all that we've done, we save the positions inside the X sun, Y sun. Right here, yeah. So we'll just save this current position for later graphing. And finally, the last block of code, simulate. Okay, so what we have is the actual simulation. The first 3 lines of code is for creating the actual figures. That's like boilerplate code. It's just to set up the environment you're actually going to create the plots. The important part is the animate function. With the animate function, what this does is it takes a current time step in the animation, and that's what I stands for. And then it will clear the graph. Then we do the physics simulation a couple times. In this case, 100. We have a 4 in range loop to get some meaningful like distance of all the planets. And we'll just continue to plot them. And this extra little argument, extra little arguments at the end is just setting up the like represents the planet, the dot that represents the planets at the end of their orbits. And once we do that, we just return the axis object, which you can think of as returning the frame. And animate basically draws the frame and then it returns back to the full boilerplate code that does the animation actually and compiles it all into a simulation video. We do this like for in range to make this more like time efficient. And the last two lines of code actually put everything together in the animate function, like how many frames you want, how slow we want it, and what intervals. The higher the interval number, the slower it'll go, the animation will go. So you end up getting an animation of planets orbiting the sun. And right here, the inner circle will be Venus, obviously, and the outer circle, it will be Earth. And then right here, we just have like a photo of like the whole thing as it finishes. Yeah, and so right here is all the math, and this makes sense that they're in like these orbits, and here you can see all the time or the distances here. You have pretty large distances. So yeah, this is my code, and I hope you enjoyed the presentation. Thank you so much.